We present Bayesian optimization for sample-efficient policy improvement and robotic manipulation. Learning complex robotic manipulation from pure robotic exploration is prohibitively expensive, and even more so in sparse reward reinforcement learning settings. Thus, imitation learning has emerged as a prevalent technique for initializing robotic manipulation policies. While imitation learning does improve robotic performance, it also relies on a dataset of human demonstrations, which are costly to collect. In addition, the initial policy typically requires improvement, which means running it on a robot and collecting feedback from the environment. Especially with a real robotic system, this implies an additional massive time commitment. Thus, the challenge of imitation learning is to initialize from as few demonstrations and improve with as few additional exploration steps as possible. In this work, we present a framing of a sparse RL problem as black box optimization. We introduce a low-dimensional GMM update to aid policy improvement. We demonstrate the effectiveness of our approach in simulated and real-world robotic tasks. We start with a base policy modeled as a GMM fitted to an initial set of human demonstrations. This policy is updated using a delta to form the full policy used by our robot. We let the policy run for j episodes and average the sparse returns that we receive from the environment. We encapsulate this process as a function, which serves as the objective maximized by the optimizer. The return obtained by an update is collected in a dataset and used by the optimizer to model a distribution of possible returns. Using expected improvement, the optimizer draws a new update and lets the evaluation function determine its value. Our GMMs model the association of a state to its derivative. They consist of an activation weight per component, the component's means, and the covariances of each component. We update these GMM parameters using different schemes. The weights are updated with a simple addition and renormalization. The means are updated solely additively. The challenge with the covariances is that they grow quadratically with the size of the state. This is problematic for Bayesian optimization as it works best with a small number of parameters. We keep the growth in check by first only updating the state derivative variance, as it is the only parameter set used for inference. We then propose updating the remaining parameters either by scaling their eigen decomposition or by performing a simple Euler rotation. Both methods are linear with respect to the size of the state space. We evaluate our approach in 3 scenarios in both simulation and real world, in which the robot has to open a hatch, a drawer, and a door. The agent is rewarded only with a sparse success or failure signal. We compare our approach against 2 baselines. The first is online GMM, a naive baseline in which we simply refit the base GMM model to additionally gathered successful trajectories. The second is our previous approach SAC-GMM. It also proposes GMM updates, but does so at regular intervals during the execution based on environmental observations using a SAC agent. All approaches start from the same GMM policy. We run all approaches for a maximum of 500 episodes and track the final model success and the number of episodes needed to achieve 80% success. We fit the initial GMM policy to 10 teleoperated demonstrations for the tasks. In our simulated experiments, we find that BOpt-GMM achieves 80% success 40% earlier than SAC-GMM. SAC-GMM, on the other hand, achieves higher overall performance. We also find that both methods work best with our newly proposed GMM covariance updates. The combination of updating both means and covariances performs worse than just our update. Our online GMM baseline is not able to compete with these results. In our real-world experiments, we apply our approach to similar setups as in our simulations and compare once more to SAC-GMM. We find again that BOpt-GMM is faster than SAC-GMM. Here we give a brief impression of the difference between the initial GMM policy and the one yielded by optimization. We conclude that we were successful in applying black box optimization for efficient GMM-based policy improvement. We demonstrated our low-dimensional updates to be very successful both for BOpt-GMM and SAC-GMM. Going forward, we see potential for combining both BOpt-GMM and SAC-GMM for optimizing a policy together. Further, we think more informed stopping criteria for BOpt could be derived to stop the exploration early. For a more detailed understanding of our approach and a more thorough discussion of our results and the insights we draw from them, we refer you to our full manuscript.